Okay, please carry on.
Yeah, welcome back everybody, and I think the plan here will be very similar, but now we will talk about the number of tasks or cores, not anymore about the memory, but the motivations are very similar. Also, the plan will be very similar. We will do a bit of demo here, discussion, motivation. Then again, we have a exercise. I also forgot to say that this works both on Saga and From, so you can actually take the machine that you prefer better. Similar path, this has changed. Also there is a README, also there is like one possible solution. And then after that session, we will come back and more questions and answers and discussion. And I really hope that we get lots of questions coming in. I think we already broke the record almost from yesterday. We have now 16 questions. Hopefully we get many, many, many more. So the break is over. Now we are in this part, how to choose the number of cores. And if you want to open it up on the other half of your screen, you can. And what will we see there? It's, again, there will be a couple of methods, but I will show you maybe the simplest one to find out. But before we discuss the methods, we can again discuss motivation. Why do we do this? Why do we have the session? Why does it matter for you? Why does it matter for us? It matters because if in your job script you can ask for 1 core, 4 cores, 40 cores, or 400 cores, but the scheduler doesn't know how many you will really use. It will allocate them and reserve them until your job finishes, and only when your job is finished, then they become available for other people. So if I ask for way too many, it will block resources from others. It will also charge you more because we typically pay for the compute time, which is then multiplied by the number of cores. So it matters for you, it matters for us. And it is, if this is your own code, you probably have a good idea of how it scales, but it can be still good to verify. Also, if you see that on the website it says that code so-and-so can run in parallel or scale well, it can really depend on what we do with the code. Many big codes can do very different things, and it can depend on the system size, it can depend on what kind of features we use, whether this is scaling at all or scaling fantastically.
Yeah, and sometimes you also just have to put by hand, like you have to specify the number of threads or something, and otherwise it will only use one. Or at least you will use all. That's like the two options you usually have if it auto scales.
Yeah, or it starts lots of threads and they are all fighting over. They are all squeezed together on, I don't know, one node or one core. So all of this can happen. So it's good to verify. It's good to calibrate. Again, we don't have to calibrate it every single time we want to run something. It's more when we move to a new machine. It's when we move to a new program, or when we go from one system that we know really well to a different system with different dimensions, different input parameters, then it's good to calibrate. And it can be really good. It's good to verify. I've also seen many times that there is the expectation that just because we are on a supercomputer, which has, I don't know how many thousand cores, that if I ask for many cores, it will always be able to use it. And it really depends on the program. Some codes cannot use more than one, even if I ask them to give me many. So we want to verify, we want to calibrate. There are many ways, and also on this page, there are things that we will not discuss today, but it can be an interesting page to read through. There are examples on, maybe we'll have time later, but I maybe don't think so that we will go through all of these examples. But I invite you to to have a look. If you use Python or R MATLAB, how can you then find out that can this run in parallel or not? How about libraries? So these are things we will not go into. We will also not have time to discuss like how can you find out whether this is MPI parallelized, OpenMP parallelized. One problem with many documentations, and I think also a little bit including our documentation, is that when you are new to the cluster and you want to run a job, there are examples and they tell you that if this is an MPI calculation, then use this script. If this is an OpenMP calculation, then use the other script, but it can be very difficult to even tell. But
but just like a general, do you think like if I'm a user and I use some software, how high is the chance that it actually runs on multiple cores or multiple nodes? Or so how is it something like does most of the software run in parallel and I don't have to deal with that? Or is it that and they can just like ask for 2 nodes or 40 cores or something? Yeah. Or is it something which like you should actually like look into because there's a high chance that it doesn't?
So I think that most software does not use more than 1 core, but I also think that maybe 10% of software uses 90% of the resources. So most of the software that actually uses the resources that we have runs in parallel. But most users, but this is a little bit anecdotal. I don't have really solid data on it, but I would suspect that many applications that are running on our cluster are not using more than 1 core, which maybe not most, but many. And this is not even a problem because then they can be parallelized with other means, like with using Slurm job arrays. But what is your feeling there?
Yeah, I think similar. I mean, it depends a bit if you come from this like huge quantum chemistry packages, or you use
climate models.
Yeah, like these things are usually parallelized to the extent that they can use like multiple cores, but sometimes even multiple nodes, so multiple computers, and work together.
Yeah.
And these are our biggest customers, basically, our users. But if you, let's say you want some bioinformatics software, or you have an R script you got from someone, then there's a high chance that it will not run in parallel, or at least that you sometimes have to look into, because some software actually like has this. And the problem is also there's different names for it. Sometimes called threading, sometimes it's called cores. You have a parameter you can set, and it's something you should definitely check out. Like if you use some bioinformatics software, have a look what the input values are, and if there's something you can maybe set, like can you set threads or can you set cores? And then
yeah. And it can be.
But we can also know, like, I'm not like, so I don't know what you're now planning. So, but do you have some example where we can see if it runs with 1 or multiple cores?
So we have an example here with but I wanted to show that maybe later. So there is a Python example, which just by looking at it, can I click here? It doesn't really look like it should run in parallel, but it actually does. If I run it, because I'm using a library which can use parallelism, but it can be really hard to tell just looking at the script. And then, depending on how I launch it, it can run in parallel or not. So we could look at it in a moment.
I mean, how kind of are you trying, like, I'm not sure, will we go through some example where we can see how it looks if it's just using 1 core, if it uses multiple cores?
Yes, we can do that.
Because it's like not even like, you can sometimes test it on your own PC at home already. Like if you run it on your laptop, for example, before you go to the cluster, you can sometimes see already like this top or HTOP or one of those. But
yeah, actually, maybe we can start like that. I think we have enough time. I wasn't really planning to show this, but maybe this is actually a good example for Saga. Also, coming back to your question, are most cores parallel or not? Depends on the machine. On Betsy, definitely yes, otherwise they wouldn't be even there. On Fram, most probably yes. On Saga, there are many cores that are not. Let me create an example here, which will be a Python example. So I got this Python script from somewhere. Now you don't have to do anything. You can watch me doing this and hoping that it still works. I wrote this documentation pretty long time ago. How should I call it? Example.py. So I have this script, example.py, which does some matrix multiplication. Okay. And then I have this run script, run.sh, that's how I like to call these. And now for the moment, I did not know that what these things mean. I don't have them there. We need to adapt. What is our account again? It's 9999984. I don't need the development queue. Instead, in this, I should use reservation. Everything else looks pretty good. Yeah, I will ask for 4 cores just because I think it will be faster, but let's find out. And maybe what I would do, we can try both the Ceph, but we can also try logging into the compute node. Let me log into Saga, and let me go into this. Just have a different window here. Good. Let's launch this thing. So one thing we could do. Let's launch. Good, running. Where is it running? It's running on that one. Let's SSH into it. And one way to find out how many cores are we using is again to look at top. Takes really long time here. Top. And where is my example? Am I still running or not? Here is it. That's the one. On top here. So I'm using 12% of the CPU, but I'm seeing only one of those. So if I would see several of these, it would probably use several of these. I asked for 4, but I'm using really only one. Now I have 100% CPU, but still only one.
So what does 100% CPU mean? Because that sounds like I use everything.
Well, it means 100% of one core out of the 40 that are here. Or 20 or 40.
So if Python, the process, would use all 4 cores, it should be 400.
Yes, or I should see 4 times 100, 100, 100, 100. And we will see that example. Yeah. I think it will finish in not too many seconds. Before I adapt it, I wanted to also have a look at. I asked for 2 minutes. I think something like 1.5 minutes. And then I want to see what do we see from a Ceph. And then I will run it in a better way. But this running in a better way can be really difficult to know. So if you get a code from somewhere or script from somewhere and it promises that this thing should run on 20 cores and then you find out, well, it doesn't, then please do contact us. This can be really difficult to know here, that's the way to get more out of the Python script. Okay, it finished. What does Ceph tell us then? Well, yeah, 20% was utilized. Not too great.
So this is the average, isn't it? The average of all the CPU cores you asked for.
Yes.
So they're combined. So yeah, we use 20% of the 100 we asked for. Not great.
So ideally it should be, well, if the one was constantly busy, it will be 25, but still we want to have more than 20, because here 80% did nothing. And in this particular case, I will get more out of it by putting this in my script, because then this NumPy, which is this numerical Python library, can run in parallel, because that one uses a parallelized math library under the hood. And in this case, I'm making sure that these match up with this, what I asked for. And
you
now
can
let's run.
Slurm also sets some variables, so you could also, if you change sometimes from 4 till 8 or something, and you don't want to like do it by hand, and which always there's a risk that you forget one of them, you can also set them to a Slurm variable.
That's a great info, and I can never remember them, but they are good to know. Slurm variables, Slurm variable, Slurm.
I mean, we can also SSH we can also SSH into the job to see which variables are set in that moment. Aber there you see.
Yeah, so that was
here,
very
this
good.
one, the OMP num thread, the last one is the one which you often want to set if you.
Yeah, so it's instead here I was just lazy, but what would have been nicer, what Jon meant is that I could, instead of setting 4 here, I could set this to some Slurm variables that are defined by the job. Yeah. Then I only have to change this and it will always work. But let me test it out.
Because we see this a lot, that people like that, you know, you see a job script and then it contains still hard-coded variables like the number of cores or something, which we know are from some old generation computer. Because like Slurm job scripts are inherited or like moved from one, if they work, and I understand that they moved from one compute cluster to the next, but sometimes the amount of memory changes, the amount of cores available changes, and then it's always good if you move something, or if you get something from a colleague. If you are now in this course and you have gotten job scripts from a colleague, maybe now with the new knowledge, and go through them and actually check if all the variables make sense, and if like use Ceph and all these tools.
Yeah, and now I'm oh yeah, that it was briefly. I could see 340%. Yeah. That's good. Oh. There it is. So this example will take less time. And so it's either this, or to see lots of similar jobs that each use 100%. That's what you want to see. And yeah, it finished. And if I would compare the, well, let's have a look. Ceph. Here it's already not amazing, but it's the total time to completion was shorter. It's not this is not the most amazing example, but I have a better example which you can then also look in. That will be part of your exercise. And in this example, there is again a mystery binary, and we don't know here in the run script, should I ask for 4 or 40 or 60 or 200? If I run this script, it will take approximately a few seconds to 1 minute, 2 minutes, depending on how much I ask. And one way to, I think maybe the simplest way, but also the most reliable way to have a feeling for how many cores you need is, and Ole has shown that yesterday and today, is to run a series of calculations with 1 and 2 and 4 and 8, 16, 32. It doesn't have to be a multiple of 2, but I think computer science people like multiples of 2. 32, 64, 128, or in case of Saga, maybe it would make sense to test 20, 40, 80. And then look at how long it took. And this is exactly what we will do in this exercise. So in the exercise, and I want to show you what you will find there. Where is it? In here. What you will do is you will again copy an example to your favorite place. For instance, here. What is nice is that I already prepared a couple of run scripts for you, and you will see you can see immediately what they mean. We run the same job, the same binary on different numbers of cores. We don't really specify where they should be. So if I look at one of these current scripts, I don't really specify that they should be all on the same node or not. In this case, I don't care. I specify I want to have 64 of those. I don't have to repeat the information here. srun will understand that I wanted 64. Also, to make it then easier to compare the outputs, I have renamed the output to the number of cores that you use here. This is available both on Saga and on Fram, so you can run it on either of the two machines. And what your goal is to run this series of calculations and look at the timing. Well, on the README, so there are some instructions. Copy this folder, submit the run scripts. Then one convenient way is to grep for this text in all the output files, and then look at the last column, and it will, I mean, I can already give you a little spoiler, because, so if you look at the spoiler, you will get something that looks like this, hopefully. So output and how long it took, and let's clear the spoiler away. And based on that, your goal is to find out what is a good setting for this particular job. Does it make sense to ask for 128 cores? And you will find out, well, I will not, you will find out. So that's your goal, to find out what is an optimal setting in this case. If you have time left, you can try the same thing on your favorite code. And again, we will give you 15 minutes. Again, please, here in the collaborative document, let us know if you would like more time. Again, you can participate here in the main room, or you can join one of the breakout rooms where you can then discuss and screen share without any recording.
Yeah,
did I make the exercise feeling that something is not going too great there? I don't know if this was also your observation. What's going on Fram? Yeah, I think better, but I need to wait a bit, because so I think this example works today better on Fram. What you will see when you run all of these, and you can also try that later, and what is also nice is that really we have this example also nicely documented here. And what you will see, maybe you will see something like this. Oops. Where was the table? I ran this example yesterday evening, and this is what I got. On one core, it took a little bit over 5 minutes. On 2 cores, half of the time, great. I doubled the number of cores, again, half the time halved, fantastic. This is when, if we remember the nice plot that Ole showed, we are still in the linear regime. We double the number of cores, we halve the time. But as I go further, you will see that it doesn't, at some point it stops improving. So here it reduced, here I doubled the cores, but it's a little bit more than half. Then I doubled the cores, but now what was it? I forgot the name, but it like flattens off. And as I go beyond 32, so adding 64, things actually take longer. So it's not only will I pay twice as much, but it will even take longer time. And then going to 128 cores, it really completely reverses. So if I saw something like this, what would I choose? I would choose probably 8 or 16, maybe 16, maybe 8. This could be a good setting, or less. I mean, if you have a lot of time and you don't need so 1 to 16 could be a good setting. Going beyond 16 in this case for this example doesn't make sense. And maybe you saw that as well. And if it didn't work for you on Saga, then I'm really sorry, because we had trouble yesterday on the file system with backup. I don't know whether this still is ongoing, but then you can test it out this afternoon or tomorrow, and you can also test it on From. The same example, everything's the same. I'm just wondering whether there are any questions we should discuss. Maybe we should take a break first, and then after the break we will still have we can do a Q&A session.
Yeah, that would be great. Maybe we could take a 10 minutes break until 12:10.
Yep.
Yeah. Please ask more questions here.
Yes, looking forward to the last 20 minutes.
Yes.
We will discuss a little bit more, try to clarify some of the things that came up. Also, at the bottom of the document, please give us this feedback. This is really one of the few ways we can improve. We would like to know not only what was nice, but also what we can change, remove, improve, add until tomorrow and next events. So it will be very nice to hear here. Over the break, I thought maybe we should clarify before moving on. We saw that at some point, adding more and more and more cores, it didn't really help here anything. But how can that even be? How can it be that? Shouldn't it be that adding more processors should make things better? How can it then take longer again? We saw that after 16 cores, after 32, it takes more time than less. How is that possible? And I think this is good to understand. And
I think there's many different reasons why this can happen. But one of this ideas I had when I saw this is that it could be, for example, I think this is an MPI program you showed here, because otherwise it wouldn't work probably over 64 and 128.
Right.
And MPI means sending data from one process, one task to another. And if they're on the same computer and the same node, this is faster than if it's spread over different nodes. And the more you spread it, it doesn't necessarily get faster if you spread it like that. So it could be that 32, for example, still fit in one node, and then with 64 you have to go to 2 or more, and then suddenly you have more just waiting for the network to send and receive messages.
Yeah, exactly. So in this case, it's we have certain work to do which takes 5 minutes on one core, and now we distribute the work. But we also need to coordinate. So these tasks need to be coordinated. We need to send messages. And at some point, the coordination takes more time than the actual work. And maybe some of you will recognize it, that in the last 2-3 years, we have spent a lot of time in Zoom meetings. And if you add more and more people to a project, at some point, all of the time goes into coordination. And this is really similar for, this is what is happening here. There could be other reasons. It could be that each of these processes need to do a lot of memory access, and there is a certain bandwidth to it, and the bandwidth could get saturated. This is not the case here. I have another example on the page that I will not show, where one can one can maybe see the effect of memory bandwidth. But it already from here we see that these are not independent jobs. They are not running completely independently. They do some kind of talking to each other.
Something which also sometimes a problem can only be parallelized to a certain extent. You have this maybe a matrix which you have to split into, and at some point there's it doesn't make more sense to split it, and then sometimes programs break after a certain, not the better written ones, but I've written stuff myself which broke if you didn't use the right number, and can be that there's just too much.
Yeah,
while you were chatting, I foresaw this, so I ran the ARM performance reporter on this one, which is always a nice tool to run. and it spent 9.3% computing, 90.7% in MPI at 64 cores.
Yes.
Was it mostly weight or something, or it was?
I can't say that from
Okay.
the performance reporter, but you have to dig more into it. But of course, I would expect that it was weighting in some MPI things. I don't know how this program is built, if it's collective or send, receive, etc.
It's actually, the answer is here.
All to all, yeah. So
it's a silly code that computes something, and then everybody talks to everybody. So this is like the equivalent of email to all, I mean, reply to all 750,000 times. So that's what's happening.
Yeah, a note I discussed with someone in the breakout room was the confusion, especially like if you come, this also relates to question 20, like if you're from Python and R is, or also like other, I often say bioinformatics software because this is like where I see it most often, is people get confused with tasks and cores and what should you use, and nodes and like all of that. Threads sometimes are also mentioned, and yeah, I think this nomenclature is really confusing. It took me also some time to really like figure out which is what. But can we give some like Radovan, do you know some tips and tricks or like how to explain it, and also like what people like who use these kind of software, maybe like Python or something, what should they ask for in the Slurm job script? If you're talking, we can't hear you.
Okay, I was I was giving a very clever answer, but it got lost in my microphone. So great question. Here's an example. I asked for 32 tasks. So what is that thing? And in this case, it meant that I get 32 cores, and I don't care where they are. But it could matter. And maybe let's take a step back and let's think of Python and R, and let's think of what are maybe the main ways to parallelize. And the simplest way, if your calculation allows it, is to not parallelize at all, but to run many independent things at the same time. Maybe each of them using one core. There is nothing really bad about it. Often we don't have other choice. So we could run many of these if they are independent, if they don't need to communicate, if they don't need to coordinate, then they can run in parallel at the same time. But then we parallelize using Slurm job arrays. Or we parallelize using bash. So we parallelize outside of the code. That's one way. And then what would I ask for here?
Like as a note, like typically Python and R, I think R, I don't have Python at least, it's not a language which makes it easy to write parallel code. Or it's at least not like you don't get parallel code if you don't do something for it. So a lot of the like scripts you will find, Python scripts, are not well parallelized.
Yeah, and that is not a problem. I would say that then.
No. I mean, sometimes if you have a task which takes 4 hours to run at jobs, you could just run them all. You could spend now 2 weeks to parallelize it to take in the end 25 minutes or something. It's 32 cores, or you just start 40 at the same time.
Yeah, so it could be 40 tiny jobs, and then they start whenever they can, or you could kind of package them together into this array job. That's another way.
It's also linked in this question. In question 20.
Oh, great. Yes. So that's one way of running many small things at the same time. And then, if we can go beyond it, there are two families, two approaches. One is shared memory parallelization, and that means that the individual jobs, they talk to each other through memory. So it's like lots of workers and they have the same notebook and they write and read from it. And this is, then we talk about threads, and then OpenMP, that's one of, then we use shared memory parallelization, we talk about threads, and then we are always on the same node. I don't think, but I might be wrong, but at least it wasn't possible to do any shared memory parallelization beyond the node because they have separate memories. So if I would do shared memory parallelization, and this is the case when you do like NumPy is shared memory parallelized, then I would specify how many nodes I want. I would do one node. I cannot go beyond one node. And then I can say within the one node, I would ask for a certain amount of cores.
So you would set nodes to one and tasks. Would you use task or cores, or how would you do that?
Is there something like tasks per node?
Yeah, there's also task per node, I think.
Yeah. So I think I would use node. Yeah.
Yeah, I think if you set n tasks to one and nodes to one, you will just get like one, because task comes mostly from MPI parallelization.
Yeah.
And then you can use, and now I'm not sure, is it cores or CPUs per task? One of the two. And I'm never sure which one.
So I use task per node or node. So now to summarize, we have this. One is they are completely independent. We use job arrays. The approach 2 is shared memory. It's OpenMP threads. So then we talk about threads. Oh, and we are always on one node. And then the third family are MPI jobs, like the one here. And then it can be, they don't have to be on the same node. It may or may not matter to the performance, whether they are on the same node. If they do a lot of communication, it may matter because the communication within the node is easier than across nodes. But then we talk about tasks. Ranks is the same thing. Then we don't talk about threads, although it's a similar idea. But then we talk about tasks, workers, ranks, and they don't talk to each other through memory. They don't have a shared notebook. They send each other messages. So little envelopes with messages, but they have each their own memory. They do their own thing and they coordinate by sending messages. And this is what I was, in this example that we ran here, this is what was going on. But here the point was not to dwell on like what is MPI or not. I wanted to show you an example, which is rather typical, is that very often as soon as we go to larger core counts, communication takes over and dominates computation, and that's what we don't want.
Someone, here's question 21, and it's quite, what if you get someone's script and you want to run it, you want to figure it out. I mean, we showed a bit already in the beginning how to do that. You can run it and just like you can ask for 4 cores and then just like use top to see how many are used. Or you can use SEF, like Ceph in the end, to see if you ask for 4 cores, but the average was like 20%, then it will not have used like more than 1, probably, at least not for like an amount of time which is like that's worth it. So then I would just say like use 1 core and maybe use this job array to Slurm job array to make like start multiple of these in the same time. Yeah, and like if you also, if it's not a script, but you use bioinformatics software or like any kind of software you use, basically just you put some input files in the software and you get it out, and you don't know, use SEF, use top, use these things we also described in the documentation. And if you're really unsure if you use like tasks or something MPI, I would actually just like open the web page or like the GitHub or like documentation and look for MPI. If it mentions MPI, there's a chance that it will like, there's a good chance that like n tasks and multiple nodes will work for you. But if it's Python software, it's probably, or like R software, it's probably not the case. Most of them are intended for, you know, 1 computer.
Yes.
Or even just 1 core.
That was a great question. Also, somebody selected the entire document. That is dangerous because if you hit a key, it will replace everything by that key. So maybe unselect. Any other questions coming in? Also, please, since we close in 5 minutes, please do give us feedback. No feedback at all. It's a bit like when you give a scientific presentation and there is 0 questions at the end. Then you know that that was not good.
Yeah, so we can't even hear you. We can't even hear the audience snore. Yeah. Like in a real, like in a room, you can see people falling asleep.
Yeah.
You don't get anything.
And we can also mention that tomorrow you will. Oh, sorry, I have a kid at home, so maybe it's a bit noisy here. But tomorrow we will learn how to install software on HPC if it's not already available as a module. So.
Yeah, I hope the last part was now not too rambly, because I think we jumped a bit around. Next time we should maybe focus a little.
What else should we clarify before we close the day? So tomorrow, software installation. Are we also going to learn how the module system works? I'm just updating myself.
Yeah, I mean, we already did that in the last course as well a bit, but I think we will mention again, like how to search for a module, how to install it, how to load it.
And not only, so we will learn about easy build and about installing Python packages, installing R packages, and also a session on containers, so Singularity on high performance computing, so Singularity on our clusters. So these are really nice technologies. Really looking forward. Before we close the day, tell us one thing that you liked. Hopefully there was one thing, and tell us one thing we should change, because there is always one thing we should change. And some of these we may already implement until tomorrow, so it's really good to know. And if no other questions are coming in, then I think I'm happy and we can conclude. Any final remarks before we close the day?
Not much, but I would like to thank Radovan, Ule, and Jon for these sessions, and I hope everyone enjoyed these sessions and learned something, and you have something to take away with you. And thank you for your time, and I wish all of you see all of you tomorrow as well, and that will be some interesting sessions on software installation. Yes, feedbacks are very important for us, so please give us free feedbacks. And thank you for today, and see you tomorrow. That's the final day of the course. Yeah, that's all. Thank you. I will end the meeting at 12:30 exactly. Thank you.